Greetings and welcome back. Today we'll be looking at some reactions that we've previously done, discussing them in terms of both their kinetics and their thermodynamics. So oftentimes with a reaction we can get multiple products, and we've seen this before in SN1 and elimination reactions. But as we move into more advanced addition reactions, we again have to consider what our possible products are. Sometimes that's based on the thermodynamics of the overall reaction, and sometimes it's based on the kinetics. These are two things that we've talked about already. If you haven't watched the video on kinetics and thermodynamics or remember everything about these from general chemistry, I would highly suggest you go back to those and watch those first. But that being said, we're going to now apply what we know about kinetics and thermodynamics to reactions that can give multiple products. So the first thing I'd like to do is define again thermodynamics and kinetics. So thermodynamics in terms of a product is going to be, in general, the reaction or the product with the most negative delta G. That is to say, the most exergonic reaction. And usually what we're talking about is the most stable product. So for instance, if we start a reaction here and we have our little hump and we go down to a product, or we could possibly also do a different way, this would be down here your thermodynamic product, because it is the lowest energy and has the largest negative delta G. That is to say, it goes down in energy the most. All right, so when we're talking about a kinetic product, what we're considering is rate of a reaction. And rate of the reaction depends on the energy that is required to overcome those barriers. Usually the barrier that we have to overcome is the activation energy. It's also possible that you could have a very high energy intermediate, which would of course mean that you have a high activation energy, but we consider both of those things. So in thinking about a kinetic product, we're thinking about the reaction that requires the lowest amount of energy to overcome the activation energy, or E sub A. And this means that this is basically the fastest reaction. And normally when you're looking at a reaction energy diagram, it has the most stable transition state or reaction intermediate. So let me give you an example here. So let's say that we have two different products that we could have, one of which takes a large amount of energy to overcome, and one of which takes a small amount of energy to overcome. This one right here would be the kinetic product. Not because it's lower energy at the end, but because of the fact that the transition states here are very different in energy. So this would be a very difficult activation energy to overcome. It would require more energy and would therefore be a generally slower reaction. And this one would be easier to overcome. What I was trying to do for both of these is, you can see in both of these drawings that the one that has the lowest activation energy often happens to have the lowest energy at the end. So the more stable intermediate here gives you the more stable product. And the same thing over here. But sometimes those things go hand in hand. A lot of times the kinetic product is the thermodynamic product as well. And a lot of times the thermodynamic product is also the kinetic product. But sometimes it's not. And sometimes it's very hard to tell which one is the thermodynamic product, but we can tell the kinetic product. So in this case, the difference in energy between those two products is not so different, right? They might actually be about the same. However, sometimes we can tease out a very big difference in energy between transition states or between intermediates. Likewise, in this reaction, the kinetics might not be very different. And so instead what we will find is that we have to base the amount of overall product on the relative energy of the comparative products that we see here. So sometimes it's based on the stability of intermediates or transition states, and sometimes it's based on the stability of products. So I'm going to give you a couple examples of this, and we will do one of them as an E2 reaction. So E2 reactions we've seen before. So here's an example right here. We have a chlorine that is a leaving group. We have the carbon next to it is an electrophile, and then the hydrogens on neighboring carbons are both acidic. So, depending on the nature of the substance we add to this, we will get either elimination or addition. So let's say that we add TBUOK. This is a bulky base that will not be a very good nucleophile, and therefore we will just get elimination. So let's look at the two different ways that we can do this. One would be for our O- to share electrons with this acid and act like a base, and therefore we would get a product that looks like this. A double bond would be right here. The other way that we could do this, and I'm going to do this in a slightly different color, so the green path, let's say, would be that we have another possible path, which would be to take off this hydrogen, make that double bond, and once again kick off the leaving group. That would give us a different product, which would just have the double bond over here. Well, our transition state, it's hard to really say which one is more stable. The transition state would be kind of halfway in between all of these. We don't have an intermediate. So we would have a difficulty figuring out which one is the kinetic product. However, we do know enough to look at those two different products and say which one is more stable. Well, we know that for an alkene, the one that has more direct carbon substituents is the more stable one. So this would be a tri-substituted alkene. And on the other hand, this would be a monosubstituted alkene, because there are 3 hydrogens and only 1 carbon directly attached to the alkene. So, we definitely know that this one is the least stable product. And we also know that this one up here is the most stable product. So let's look at the reaction energy diagrams and say what we can tell about this reaction. So overall, when we start off, we have this guy. It's the starting material for both directions. Well, we have 2 different ways we can go. We can go to the alkene that you see in yellow, which is the tri-substituted alkene. This is a lower energy product. Or we can go through to end up at the monosubstituted alkene, which we know is a less stable product. Again, it is difficult for us to look at these 2 possible products and discern which one would be the kinetic product. However, it is very simple for us to tell that comparatively, the one up here is the more substituted alkene, and therefore it is the most stable possible product, and therefore we could say that this is the thermodynamic product. All right, so that's what we can see for elimination, is that usually our major product is the thermodynamic product because it is the most stable one. So let's look at another example where we have the SN1 reaction with the possibility of rearrangement. So for SN1, to model SN1, we will use the exact same starting material, the same alkyl halide as the reaction before. However, what we'd like to do in order to do an SN1 reaction is add in a very weak nucleophile, so we'll just add in water. And what we'll find is that we can follow multiple paths to get to multiple products. We would have one path in which the leaving group leaves all by itself, and we would have this intermediate right here. And then the water would go on, and then we would deprotonate. I'm not going to go through this mechanism all over again, but we would end up with the alcohol right here, because the nucleophile, which is water, would add on to that carbocation spot. The other route that we could follow, which I will do in pink, is that we could follow the route in which this guy leaves, but a rearrangement occurs in which a hydride shifts over here. That would give us a carbocation at this spot. And then for the rest of the mechanism, we would add in our water. It would act like a nucleophile, become a protonated alcohol attached, which we could deprotonate just to become a normal alcohol. So those are our two possible products. And looking at those two alcohols, there's not a really good way to tell the difference between them. However, what we can do is tell the difference between the energy of the intermediates. The one that I've drawn in blue is a secondary carbocation. The one that I've drawn in pink is a tertiary carbocation. So let's look at the reaction energy diagrams for this. We're starting again with that alkyl halide, which we'll just put somewhere. And then for our blue route, we went through relatively unstable intermediate. We ended up with a more stable product, which is this guy right here. All right, and here's my intermediate. I'll draw it like this. It's our secondary carbocation. Well, comparatively, the pink route doesn't give us a easily recognizably different energy product. That is to say, the product of the pink route is about the same energy as the product of the blue route. But we do know that the energy of the intermediate is far lower because a tertiary carbocation is much more stable than a secondary. So what can we say at this point in terms of our thermodynamic product and our kinetic product? All right, so we can't really tell which one is the kinetic product or the thermodynamic product because we can't really say for sure which one is a lower energy or more stable alcohol. They're probably about the same stability. However, we can definitely tell that the pink route goes through the more stable intermediate, and therefore it would be easier to go through that pink route, and therefore, for sure, this is going to be your kinetic product. And we don't know very readily which one is the thermodynamic product. Similarly to in the last slide, we don't know for sure which one was the kinetic product. So sometimes you can tell a kinetic product, sometimes you can tell a thermodynamic product, sometimes you can tell that they're the same thing, sometimes you can tell that they're both different things. So we will move into this in class when we consider addition reactions. Thank you very much. I've got a problem for you to practice really quickly. And please bring any questions with you to class. Thanks.